this video, we're going to look at the acid-catalyzed hydrolysis of amides. And so amides are not particularly reactive, so you're looking at something with this general structure. And I drew a primary amide by putting 2 hydrogens on the nitrogen. You could also have up to 2 R groups on that nitrogen as well, and it would still be part of this same functional group. So these are, as we said, not very reactive, and that's because you do not have a good leaving group. To react this neutral amide, you would have to kick off NH2-, which is a really, really strong base. And so if we want to have this amide undergo a hydrolysis reaction, we're going to have to force it to occur. Which, as your textbook author points out, this is actually kind of a comforting thing to know that amides are not really reactive, because the proteins in our body are held together by peptide bonds, which are actually amide bonds. So we don't want those just falling apart in any aqueous solution like our bodies, which are, majority water. So anyway, if we're going to do an acid-catalyzed amide hydrolysis, we are doing this with water and some kind of strong acid. And we usually have to heat this up as well. So we might actually just represent this as like water and a strong acid, or it might just say H3O+. But that's going to be what's going to be our hydrolysis. So to predict the product of a hydrolysis reaction is pretty simple. No matter what group you have here, no matter what's attached to your nitrogen, if you're doing the hydrolysis, you're replacing that with an OH to make the carboxylic acid. All right, so you're going to get the carboxylic acid. And if you're asked for a major organic product, you're probably looking for that. And you're also going to kick off this amine. And in acidic solution, it's not going to exist as an amine. It's going to exist as the ammonium salt. So it's actually, in this case, going to end up being NH4+. And that would probably have whatever counter ion came along with your acid, right? So if your acid was HCl, then you would have ammonium chloride. So you're always going to have this ammonium salt that forms as well. Okay, so predicting the product is fairly straightforward. The mechanism it's not unstraightforward, but it is long, like all of our acid-catalyzed mechanisms. So let's look at a specific example. Let's start adding some groups to this amide instead of just saying R. Okay, so let's just say we have a 4-carbon atom amide, and let's throw a group on that, right? So if we wanted to name this on the nitrogen, we have an ethyl group. So this is N-ethyl. And it's 1, 2, 3, 4 carbon atoms. So if it was a carboxylic acid, it would be butanoic acid. And since it's an amide, then it's butanamide. Butanamide. So if we were to take this and we were to subject this to a hydrolysis reaction, right? So we use some sort of aqueous strong acid and heat. So we're going to get the carboxylic acid. All right, so I'm just taking this portion and replacing that leaving group. So I should have labeled this, I guess, as a leaving group. And so that's going to be the leaving group, and we're going to replace it with an OH. And then we would have this amine as the ammonium salt. So it's going to end up gaining in the course of this reaction 2 hydrogens to give us that ammonium salt. So let's take a look at how this mechanism works. And it is going to be long, a lot of proton transfers. So before we get started, we should take a look at this solution. If we're going to be moving protons around, we want to know what we really have. So we're going to have a small amount of H3O+, because you probably only dissolved a catalytic amount of strong acid, and so that would be functioning as an acid. So anytime you find yourself needing to add a proton in the mechanism, you're going to use H3O+ to do that. And the only thing you're going to have available in this solution to act as a base or a nucleophile, at least at the very start, would be the conjugate base, which is water. So if we need a base or a nucleophile, this is what we're going to use for most of the mechanism. And I say most of the mechanism because at some point in time, you're going to also have an amine base in there, which is going to grab a proton. But until you've actually kicked off that leaving group, you're going to be using just water as your base or nucleophile. Okay, so let's start with that N-ethyl butanamide. Okay, so we're going to redraw that structure. And in every acid catalyzed reaction that we're going to see in this chapter, these nucleophilic acyl substitutions, if you've got an acid catalyst, the very first thing you're going to do is you're going to protonate your carbonyl oxygen with that catalyst. So we always do this as a first step under acidic catalysis. So we're protonating that oxygen, and that's going to do a couple of things. It makes this carbonyl carbon more electrophilic, right? And also having that oxygen protonated means that after you attack the carbonyl oxygen, you won't be generating a negative charge, because when our nucleophile attacks, so that's going to be the next step, is we're going to have water as a nucleophile, is going to attack this carbonyl carbon. When we push these electrons up onto here, we want to make sure that it's already protonated so that we're not forming a negative charge. Because in acidic solution, an oxygen anion would just be too strong of a base. It can't physically exist in this sort of a solution. All right, so we have attacked the carbonyl, so we're going to get to a tetrahedral addition intermediate. So we've got OH, so tetrahedral because the geometry of this carbon has gone from sp2 to sp3, so it is tetrahedral. And we're going to have this water molecule that we just added. All right, so what we want to do is we want to transfer some protons around here because we want to get to where we can have this nitrogen being a good leaving group. And so we're under acid catalyzed conditions, so it's somewhat acidic, but it's not super acidic. So if I want this nitrogen protonated, I'm going to deprotonate the water first. It's not going to be acidic enough to have a 2 positive charge overall. So I want to deprotonate this water, so I'm going to say, okay, well, I have water available as a base. So I can deprotonate here. And these are the proton transfer steps that make these acid catalyzed mechanisms just a little bit long. Okay, so now we've got the OH, we've still got our NH, and now we have just OH attached. So we get to this neutral tetrahedral addition intermediate. And so I think some of your homework problems ask you about drawing the neutral tetrahedral intermediate. So that's what they mean, something like this that has no charge. All right, and so we're not set up to have nitrogen leave as a leaving group just yet. I mean, out of the leaving groups on here right now, OH minus would actually be a better leaving group, but neither of these are leaving groups in acidic solutions, so we're going to need to protonate that nitrogen. So the next thing that's going to happen is we're going to use some more of that H3O plus to protonate the nitrogen. All right, and it is overall a catalyzed process, so we don't actually consume the H3O plus in this reaction. You'll notice we use it, we reform it, we use it again, we're going to reform it again. That's kind of the pattern of these mechanisms. So we're protonating this so that it's going to become a good leaving group. So now our nitrogen has a positive charge. So it can leave as a neutral amine, which is much better than trying to kick it off as a negatively charged anion, because that would be a very strong base, definitely not going to happen in acidic solution. All right, so we've made our good leaving group, so we can reform the pi bond, and technically you could use either one of these oxygens. There's no reason to pick one or the other, because either way you're going to be reforming the pi bond, which would be the carbonyl essentially that's going to be in your carboxylic acid. So we reform that bond, and we're going to break the bond to the leaving group. All right, and so we've kicked off that leaving group, and we're actually really, really close to having the product here. So we've got a double bond to an oxygen, and that oxygen has a hydrogen. And we have the OH. Right, so this basically looks like a protonated carboxylic acid, and we've also kicked off an amine. So here is the amine that we've kicked off. So we see NH2, so this is a neutral amine, and this is a strong enough base that it's going to deprotonate this protonated carboxylic acid. So this is how you generate the ammonium salt that's also formed in this reaction. So we're going to deprotonate here and give these electrons back to the carbonyl oxygen. And so overall, right, we've gotten to the neutral carboxylic acid, And we have the ammonium salt that has formed, right? And then the counter ion to that salt would be whatever your acid, if you use like HCl, it would be like chloride or something like that. And so one thing I did draw wrong here, this should not be an equilibrium arrow. So once we get to this acid-base reaction, this acid-base reaction is favorable. So I'm going to get rid of that arrow and show it as just going in one direction.